apologizes for the kind invitation. Great pleasure to be here, of course. So my work is based on joint work with Anton and Alexeyev, and I apologize for the long title, and also apologize that there's no quantization in this talk. Maybe this is still something to come in future years. All right, so this work started out with some suggestion of Anton that we should look at some then recent papers in mathematical physics. Papers on JT gravity and ADS2. Because for me that was somewhat scary because I had no idea whatsoever what those words actually mean. But then again, he didn't ask me to actually read those papers, he just asked me to look at those papers. So the papers, maybe I should give some references. So there was especially paper by Saad, Schenker, Stanford in 2016, a paper by Stanford and Bitten in 2016, and also 19, sorry, and also some paper by Meinrenken. So Stanford somehow is always involved, but there are also some papers without Stanford. So there's many papers in this direction into some sort of machinery. So as I said, there were interesting pictures in those papers. Even if I don't understand the words so much, the pictures look very intriguing. What they were looking at were some Riemann surfaces, but Riemann surfaces that are not compact, that are allowed to develop funnel ends. If you remember, you saw these kind of funnel ends briefly in Teschner's talk on Monday. These are non-compact Riemann surfaces. And what they did was, well, somehow, I understand vaguely that they have to define some partition function which involves an integral over these Riemann surfaces. And there's a problem because they're not compact, the integral doesn't actually converge. So to get around that problem, what they're doing is, they say no problem, we just cut off the boundary. They introduce these boundary wiggles, and they just cut off the boundary like that. So they produce something compact. And eventually they will let the boundary go to zero. Now, of course, there's then another problem that everything now depends on the choice of wiggly boundary. But then they say, no problem, we just take a path integral over all boundary wiggles. And at that stage, I mean, mathematically, it seems a little bit, well, risky, let's put it that way. But it turns out they seem to get a lot of interesting mathematics out of it. So some of the words that appear in their papers is Schwarzian derivatives, Piazzaro algebra, some Delson-Heckman measures, and what else? Mirzakhani volume formulas, and recursion relations, and all that. So it seems like there's something interesting going on there. And well, our modest goal was to at least understand some of the symplectic geometry that's in this picture. So the 95%, probably more of the papers we still don't understand, but some of the symplectic geometry we will have some interpretation of. Remains to be seen if it actually has some relevance to what they're doing, but our take on it is the following. And so I want to say this as our results. So following Anton's example, I've tried to be organized, but I'm just putting numbers. Right, so let's state as a theorem. So the theorem is that what we're dealing with is some infinite dimensional Teichmueller space. space of hyperbolic zero matrix, which I will define in a moment. Up to diffeomorphisms which fix the boundary and just the identity component of those diffeomorphisms. So similar to the usual Teichmueller space, except we use these zero metrics, and yeah, we only look at diffeomorphisms which actually fix the boundary. So the theorem is that this infinite dimensional Teichmueller space has a natural symplectic structure. Just like the usual Teichmueller space in the case without boundary. Now on this space that still has the action of diffeomorphisms of the boundary, or more precisely, if one thinks about it, it's the universal cover of the diffeomorphisms of the boundary that still act. And this action of diffeomorphisms of the boundary, universal cover, that action is Hamiltonian.
Maybe you should change the boards.
Raise the boards. This action is Hamiltonian. There's a moment map which makes it into a Hamiltonian Verasoro space. So the moment map is some map phi, which goes from this Teichmueller space to dual of the Lie algebra of the Verasoro algebra of the boundary at level 1. So I will explain a bit what all that means. But first I should draw a box. Right, so that's kind of our main theorem. So to explain a little bit, what is a zero metric? So again, was briefly mentioned in Teichmueller's talk. So zero metric is a metric which near the boundary looks like the boundary, like the metric on the upper half plane. Well, if it's hyperbolic. So in general, a zero metric on the surface would mean the following. So let's say we have our surface with boundary, and I introduce some coordinates. X is the coordinate along the boundary, y is the coordinate in this direction, and it just means that the metric has boundary behavior 1 over y squared near the boundary. So it's 1 over y squared times an ordinary metric. So that's the shortest way of saying it. The more sophisticated way of saying it, where the name comes from, is there's this so-called zero tangent bundle. It's a metric on the so-called zero tangent bundle. The zero tangent bundle is the vector bundle whose sections are the vector fields vanishing along the boundary. This is something introduced by Maros, but we don't really need this, so you can just take this as the definition. So our hyperbolic zero metrics are just metrics which near the boundary look like the metric on the Poincare disk, or a half plane if you want. What else we have to explain is Verasoro. Well, we do everything without coordinates, so there's a coordinate-free definition of what this means, but if we introduce coordinates, then this space, which is the target of our moment map, is quadratic differentials. Quadratic differentials on a circle. So using the coordinates. And the action of diffeomorphisms is given by, well, it's easy to say what's the action of the inverse of a diffeomorphism on a quadratic differential, say f of x dx squared. And the formula is, there are two terms. One is just a pullback as a quadratic differential. This would be f prime of x squared. And then there's the term with the Schwarzian derivative. So where S is the Schwarzian derivative? This famous expression, third derivative of f prime minus 3/2 over f prime squared. So we're trying that this moment map is equivariant for diffeomorphisms with this strange action. I should maybe say that it looks like a very, very complicated action. If one does things in a coordinate-free way, it actually looks simpler. But this is the fastest way of writing it down. Any questions so far? Right. Our second result is actually an explicit description of the moment map. So let's...
Also, excuse me, what is the meaning of subscript 1 in Virasoro?
Oh, subscript 1, so... yeah, so the Virasoro algebra is central extension. So it's a circle, it's the central extension of the Lie algebra vector fields. If I dualize the map to R, and subscript 1 means the level set at 1, the preimage of 1. So that's why one gets an affine action. Okay. Yeah, so we have an explicit description of the moment map. So to describe it, I'm using my local coordinates, and I write the volume form first of all in leading order. So it's because the metric has this form 1 over y squared. It starts out something like a function over y squared dx dy plus higher order terms, more regular terms. So this is the most singular term of the volume form as you approach the boundary. So this defines some function a of x. That's one ingredient we need. And another ingredient we need is let's introduce the function k of x and y, which is the geodesic curvature of the curves y equals constant. So again, let's say again, geodesic curvature of the curve x, y goes to x plus t, y. So the level sets y equals constant. It turns out, that's the calculation. Well, if you do this calculation, for example, in the upper half plane, the level sets y equals constant, they have geodesic curvature equal to 1. And in general, what happens is that this is 1 plus terms of order y squared. And so we can define a function. We take k minus 1 and then take the coefficient of y squared. Okay, so in those terms, the formula for the volume, for the moment map is the following. So we have our hyperbolic zero metric. And I want to write down some quadratic differential, which is the moment map. The formula for it is a squared over 2 is function a times the limit y goes to 0, k of x y minus 1 over y squared. So in other words, that's the coefficient of this y squared, plus, and there's a term involving this A, which looks like Schwarzschild derivative again. That's the formula. Okay, so that's my description of results. The main results, at least. Okay, so yeah, for the rest of the talk, I just want to explain kind of our approach to how we actually construct the symplectic structure and how one computes the moment map. Any questions still? So now I really need to plan carefully with my blackboards, because my plan was to first explain the case without boundary, which is supposed to be the standard case, and then explain how we introduce the boundary. We need to focus here. I think that's part 2 now. Explanation of hyperbolic structures. At first, in the case that the surface has no boundary, in case that the boundary is empty. For the time being, we just assume no boundary. So I will try to set up things in such a way that everything generalizes nicely to the case with boundary. So, first of all, some notation. I'm going to denote by D the Poincare disk. I could work with the upper half plane or Poincare disk, doesn't make a difference. Poincare disk is slightly more convenient. With its standard hyperbolic metric, but I don't really need to write down the formula. Okay, we have the Poincare disk, and then we have the group of isometries of the Poincare disk. So it happens to be the group PSU11, but it doesn't really matter. For us, it's the group of isometries. Orientation preserving isometries of the Poincare disk. If I identify the Poincare disk with the upper half plane, then this group is identified with CSL2R. That's the group we're dealing with. So from now on, G is always going to be the group PSL2R or PSU11 if you want. Then we define a hyperbolic structure. On the surface. Again, I'm assuming the boundary of the surface is empty. I define it in terms of an atlas. Given by an atlas with charts which take values in the Poincare disk. And the transition functions are elements of isometries. The transition functions are constant elements of G. Denote by hyp sigma this set of all hyperbolic structures. And I denote by pi of sigma set of hyperbolic structures up to identity component of diffeomorphisms. Okay, yeah. One remark is here I'm defining it. I'm not really talking about the metric in this context. So the small remark is that a hyperbolic structure is actually equivalent to a hyperbolic metric. meaning Gauss curvature equal to negative form. So I can use both of these pictures. So I can work abstractly with hyperbolic structures. All right, some remarks about this definition. Of course, we all know that Teichmueller space is just some vector space. It's contractible. So some basic remarks. First of all, the Teichmueller space is just r times r plus to the power 3g minus 3 by Fenchel-Nielsen coordinates. Right, where you choose a Pan's decomposition of your surface. You represent your surface as being obtained by gluing pairs of Pans. And then what matters is the length of these the length of the separating geodesics, and so to speak, how you rotate before you stick them together. So those are the Fenchel-Nielsen coordinates. Secondly, Teichmueller space were first considered more from the perspective of complex geometry, but then it was discovered that the complex structure, this one has a Teichmueller space, and the matrix actually Taylor. So this was Lyle in 58. I think he first claimed it, and then Alfors proved it. There's a canonical Kähler structure. So in particular, a canonical symplectic structure. Then Walford in 81 discovered that in terms of Fenchel-Nielsen coordinates, this symplectic structure is just the standard one. So if you use Fenchel-Nielsen coordinates, then it's just dli wedge dti with the length parameters and the twist parameters. It's quite remarkable because the formula, of course, you could take this as a definition of the symplectic structure, but then it's surprising that this does not depend on the choice of Pan's decomposition. And then there's another approach to the symplectic structure, independently due to Goldman and Hitchin, around 87, who observed that Teichmueller space is actually a connected component of the representation variety. All right, because the group that we're dealing with here is not simply connected, it's the group PSL2R. The representation variety has several connected components. And one of those connected components is exactly Teichmueller space. But this is true also symplectically. So by Atiyah-Bott, since the Lie algebra has a metric, this space has a symplectic structure. And the symplectic structure agrees with the symplectic structure on Teichmueller space. So you could take that in principle as a definition. Right, so the two form is exactly Atiyah-Bott. But actually, we are going to give a somewhat different construction of the symplectic structures, similar to, it's also gauge theory construction, very similar to this Goldman, but a little bit different and easier, I would say. The description is more complicated, but the construction is easier. Okay, so how do we do it? Okay, construction of the symplectic structure. Okay, the first thing we fix is a principal G bundle over the surface. So this is some principal G bundle. So we know the projection by pi. It is related to this picture. I mean, here one has several connected components which correspond to flat principal G bundles of different topological types. And we fix the principal G bundle of the correct topological type. So, principal G bundles are classified by their sometimes called Euler number. With some element in the fundamental group of the group, which in this case is just the integers. And what we require is that this Euler number is exactly the Euler characteristic. So that's the component that one gets in this Goldman-Hitchin theorem. So this is the first thing we fix. And another thing we fix so we also fix what's called a developing section. A G-covariant map into the concrete disk. A developing section. So there are various ways to look at it. So one way to look at it is to such a G-covariant map can be viewed as a section of the associated bundle with fiber D, and that's why it's called a section. Another way to look at it is to remember that, well, G acts on the concrete disk, and it's a homogeneous space. It's G mod K. So you could say a developing section is equivalent to a reduction of the structure group of your principal bundle to the group K. K being SO2, is a stabilizer of any point in the Poincare disk, the center. So this will also fix. All right. And now we make a definition of what we call positive connection. So the connection, this is my notation for connections on the principal bundle. So a connection is called positive. If the following map is positive, so if you have a connection, you have a horizontal lift. It goes from the pullback of the tangent bundle to the tangent bundle of the surface. The tangent bundle of the principal bundle. So the horizontal lift. J theta, horizontal lift. And this we can compose with the tangent map to our map sigma. And this then goes to the tangent bundle of the Poincare disk. And this is then a map between rank 2 vector bundles, and I require that this is in fiber-wise an orientation preserving isomorphism. So it may seem a little bit strange to have this set up, but I should. It comes from the theory of geometric structures. If one has a hyperbolic structure on the surface, then in the theory of geometric structures, one knows one automatically gets the principal G bundle with a flat connection and a developing section. So we're kind of taking this theory that we're using in secret and returning it So there is some kind of scientific reason for making this definition. It's the horizontal lift. So the connection defines a horizontal lift of vectors. That's the definition. Right. And what is it good for? Well, if you have such a positive connection, then you get automatically a Riemannian metric. Again, this is why it's used in this theory of geometric structures. In this case, sigma gets a Riemannian metric. Why? Because there's the metric on the Poincare disk, and you just pull it back under this map. Right? So you get a metric on this bundle, and then descends to a metric on sigma. So it gets a Riemannian metric. And if the connection is flat, so this metric G, and G is hyperbolic.
About the positive definition, this developing section, how unique is it, and does?
Oh yeah, I should have said so. Of course, I'm making choices here, but everything is unique up to isomorphism, right? So the principal bundle is classified by this number up to isomorphism, and the developing section in this case is just a reduction of structure group. That's also unique up to isomorphism. So this pair p comma sigma that I'm using, it's unique up to isomorphism. So the choice is not really relevant. Any other questions? I should maybe explain why is it hyperbolic. Well, one way to look at it is you have this flat connection. So you have a horizontal foliation, right? The flat section. It gives a foliation of your principal bundle. And the positivity condition means that the map sigma takes the leaves of this horizontal foliation as a local diffeomorphisms to D in an orientation preserving way. So I can just pull back the hyperbolic metric on D to a hyperbolic metric on the horizontal foliation, and everything is G equivalent, so it descends. Right, so in this way we get some relationship between hyperbolic metric and flat connections in a very clear way. And so we can really say hyperbolic structures on the surface that's these positive connections which are flat, and then up to gauge transformations. Gauge transformations which preserve my developing section.
Is there any possibility for the flat connection we don't get hyperbolic? Do we have any cases that we have the flatness condition but we don't get the hyperbolic?
Well, you need the positivity condition. So if it's just a flat connection but not positive, then this G would be singular or something like that. That's the problem. So this positivity condition is both positivity and some transversality condition, so to speak. And the transversality condition is what you need to get actually a metric.
And it definitely works for when we don't have boundary. Otherwise, we don't have this hyperbolic thing close to the boundary.
Close to the what?
The boundaries or to the.
At the moment, we're still in the case without boundary. Yes. So most of my talk is for the case without boundary. At the moment, we don't have a boundary. I'll get to the boundary in a moment. this is just a way of phrasing hyperbolic structures in terms of flat connections. So it's, yeah, I should say, then when we go to Teichmueller space, we of course take a bigger quotient. We also quotient by diffeomorphisms of the surface, which in this language means that we don't just quotient by gauge transformation, we quotient by automorphisms. So Teichmueller space would be this space up to here. Be careful, so it should be automorphisms of P preserving sigma, and I put a subscript here which indicates that the base map should be homotopic to the identity. Right, and the upshot then, of course, is that this is actually a symplectic quotient. So this is a symplectic quotient. In this way, Teichmueller space inherits a symplectic structure. Some more space to that. So recall. Recall that the space of all connections has a symplectic structure, this famous idea about symplectic structure. It's given by just integrating over the surface. Okay, what are A and B? A and B are tangent vectors to the space of connections. And well, this is an affine space. And then a vector space is one forms on the surface with values in the associated bundle. And this bundle has a metric. So I can take two such tangent vectors, wedge them together, and then use the metric to make it into an ordinary two form, which I can then integrate over the surface. So there's the symplectic form. And using that language, the curvature essentially becomes a mole map for this action of automorphisms, and this becomes a symplectic quotient. So I can say Teichmueller space is a symplectic quotient of these positive flat connections. Positive connections on P, symplectic quotient by this group. Yeah, so you could compare to this Goldman-Hitchin construction where we have a symplectic quotient of all connections, and then by the quotients by gauge transformations, but all gauge transformations. So this description is a bit more complicated, but on the other hand, the proof is very, very, very easy. Whereas Goldman-Hitchin, that's a much deeper theorem.
Is it possible, easy or hard to recover voltage formula for the symplectic form out of that?
No, it's easy.
It's easy. Okay.
Yeah. So we know that indeed this omega which we get in this form is the usual symplectic structure, and indeed the way we prove it is Wolpert's formula can easily derive from this description. Okay, so now finally I should get to the case with boundary. That's ready for the questions. So, and now I want to do my magic with erasing and so on. So first of all, we're now in section 3 at last. And so section 3 is we allow for a boundary. Okay, so how do I define symplectic, a hyperbolic structure on a surface which is now allowed to have a boundary? So it's a manifold with boundaries, so I should use charts where the model space is space with boundary. And, well, it's kind of obvious what we do. So we just use the closed Poincare disk. This is our model space. So this captures the idea that if you look at it in terms of the metric, it should have a boundary behavior, just like the metric on the Poincare disk has a boundary behavior. That's the definition of hyperbolic structure. Okay, Teichmueller space, we have to adjust a little bit here. Space of hyperbolic structures we have, but now we're only taking the quotient by diffeomorphisms with the trivial along the boundary. And it's indeed true that a hyperbolic structure in this sense is equivalent to a hyperbolic zero metric. Not entirely obvious that this is the case, but it is true. We can prove it. So having a hyperbolic metric which near the boundary goes like 1 over y squared is equivalent to having such an atlas with charts. Right. Does it continue? Now I have to explain the construction of the symplectic structure. Okay, so we again use some principal boundary, but now we have a little problem here because if it has a boundary, then it's not so clear what it means by the topological type of the bundle. If there's a non-empty boundary, then all bundles are trivial. But we also have this developing section. So developing section we do as before. We just say it's an equivariant map into the closed Poincare disk. Before we had the Poincare disk is G mod K. Now closed Poincare disk is no longer a homogeneous space, but it's okay. We can still use it for this type of definition.
Can it still be viewed as some kind of reduction of structure on P?
It's more tricky. So, okay, so let's see. So, we remember the open Poincare disk is G mod K. The boundary of the Poincare disk is more like G mod B. So if you think in terms of PSL2R, these would be upper triangular matrices. So you could say on the interior you get a reduction of structure group to K, on the boundary you get a reduction of structure group to B. But in this formulation they actually fit together nicely. So this we have. Yeah, and it's important that we get along the boundary a reduction of the structure group to B, because this B, so again B is like the image of upper triangular matrices. So the inverse A where lambda is positive and this is some real number. So it's like this. This B is contractible, that's important. So if I reduce the structure to B, that means it's basically as good as having a trivialization. So you can think of this as defining a trivialization along the boundary. And then it makes sense again to talk about the topological type, because we now have a principal bundle together with the trivialization along the boundary. So I could say something like this. You think you trivialize it along the boundary and then maybe cap off the boundary and put in some with the trivial bundle, and then you can again define this quantum number, and it should equal the Euler characteristic. So those data we fix. Right. Continue. So now we look at our definition of positive connection. Okay, we have to use the closed Poincare disk, but other than that, it's the same definition. Okay, and how does it continue? So in this case, then sigma gets a Riemannian zero metric. So the metric, we get a zero metric because it blows up along the boundary. Again, we just pull back the zero metric which you have on the closed Poincare disk. And if the connection is flat, then this zero metric is hyperbolic. And this is then again true on the nose. The hyperbolic structures are positive flat connections up to gauge transformations. That was on the nose. But the Teichmueller space, be careful because now the base map should fix the boundary. So maybe I put it like this. So it's automorphins of the crystal module which fix this developing section, and the base map is not only homotopic to the identity but also fixes the boundary pointwise. So, okay, yeah, we would like to say that we're done, but unfortunately we're not. So, yeah, this is the symplectic portion, and unfortunately it's not true on the nose. So, yeah, almost, but unfortunately not quite true. So, what's not true? Well, we can define, as before, a T-about symplectic structure on the space of connections, and then get something on the space of flat connections. But the two form that we have actually does not descend. So it's not a symplectic portion on the nose. So it's a bit more tricky. Still one more move that we have to do. So where's that blackboard? There's that blackboard. Alright, so that part is so far so good, but this is just not true. So here we have to do some work. So again, it's not true because the two form does not descend. At least not on the nose. So a way of dealing with this problem is we just take the biggest group under which it does descend. So the reason it does not descend is that there's a boundary. If you work out the moment map for this action, there are boundary terms, and they're just not zero. That's why it doesn't descend. So instead, what we're doing is like a two-step process. We first define a space which we denote Teichmueller hat, where we take all these positive flat connections. Now we divide by automorphisms which not only fix the boundary pointwise, but also fix the entire boundary of P pointwise. Right, so really everything is along the boundary. If it fixes the boundary pointwise, there could still be a gauge transformation over the boundary. That's the problem. And here we don't allow that. So this space we can consider. This is a symplectic portion. This we can say symplectic quotient with this group. So that space we have. But then we still have on this space some leftover action. What's still acting on this space is the gauge transformations over the boundary. So the group is like this, gauge transformations of the principal bundle over the boundary, which preserves the pullback of this developing section over the boundary. And that's that. So this group still acts. And it has a moment map. And what we observe Yes, so the fact is that the image of the moment map for this action, so I don't have enough time to explain this in any detail, but this action still has a moment map. It's varies in some central extension star 1, whatever it is. So the image of this mode map is a single coordinate orbit. I mean, something like that, of course, rarely happens, but here it happens. There's just one orbit in the image. And because of that, actually, with some background in symplectic geometry, you immediately know how to deal with it. Namely, the space that we are after, that's of course Teichmueller space. This infinite dimensional Teichmueller space, which is the quotient of Teich hat of this residual action. So maybe we can do it in symplectic geometry. Is we take the product with this cogent orbit with the opposite symplectic structure. Just put a minus sign in the symplectic structure, and then quotient by the diagonal action as a symplectic quotient. And in this way, it actually does inherit a symplectic structure. Another way of putting this is this action has some mode map, whose image is a single coordinate orbit, and you could just take the pre-image of just any point in that coordinate orbit and do a symplectic reduction for that. Okay, so that's our construction of the symplectic structure. That's how it goes. And we did make some choice of this P and sigma, but again, the choice is unique isomorphism, so the symplectic structure that you get out of it does not depend on the choices. Any questions? Right, and then the last step is, of course, working out the mode map, which one then has for the isomorphisms of the boundary. So on this space, we have an action of isomorphisms of the boundary. So what happens exactly? We are looking at orientation preserving automorphisms of P, the P that we have on the surface. But the group that we're quoting by is this identity component of automorphisms preserving sigma. And this group still has the diffeomorphisms of the boundary. Or if you think about it a bit more carefully, it's actually some universal cover, having to do with the fact that we're only looking at the identity component. Not necessarily universal, it depends on the surface. So some cover of the diffeomorphisms of the boundary. And This action has a residual moment map, which one basically just calculates. So it took us some effort, but one can just calculate, because one knows what the moment map is for this, for the action of this group on the space of connections. There's a standard formula for that moment map. And this group also acts on the cotangent orbit, preserving the basically, because we're doing everything coordinate field, it's automatic that it has to preserve the symplectic form. And then one can pick out a moment map for that also. And so one just goes through the usual motions in symplectic geometry, and one just calculates what the resulting moment map is. And so after some calculation, our formula for the moment map. I think that's all I wanted to say.
Is there a fundamental reason why quadratic differentials appear in your moment map?
Why quadratic differentials appear?
So if I remember well, at the beginning you said that your moment map was...
Well, I mean, quadratic differentials, I mean, one simple reason is what is the dual of the Lie algebra of vector fields, right? So if you have a vector field and a quadratic differential, you pair them, you get a one form, and you can integrate over the circle. So yeah, so the reason is that if you're working with smooth duals, then you're looking at vector fields on one manifold, say a circle. That is the space of quadratic differentials. But here there's some central extension in the picture, so the space that one really gets is not really the space of quadratic differentials. It's this, well, level one set of the dual of the Virasoro algebra.
Should we or I don't know, we can continue with questions, or first thank Eckhart since he finished. Right, so more questions or comments?
So then where is JT?
Where's what?
JT gravity?
Oh, I still don't know JT gravity.
No, because at the beginning you mentioned...
I know, but yeah, so we just took those works as inspiration.
Oh, I see.
I was mostly looking at pictures and words and trying to use that as an inspiration. So I still don't understand JT gravity.
I have some great conflict of interest since I am both a chair and collaborator, but I can probably say some words about it, about whatever, JT. But maybe first, further questions?
Can you get, using this symplectic structure, can you get sort of some of the analogous results that they have, like you mentioned, the Mizukani?
Not yet. I mean, so first, one of the main points is what we did in our first paper on this subject. I forgot to mention, we have one paper posted on the archive from last November, and we are now working on the second paper, which maybe this November at the latest. So in the first paper, we're not really talking so much about this story. What we're mostly talking about is some correspondence between Hamiltonian Virasoro spaces and some finite dimensional spaces. So in earlier days, we had some correspondence between Hamiltonian loop group spaces and quasi-Hamiltonian G spaces, which are finite dimensional. So this is our main example of a Hamiltonian Virasoro space, and we know how to translate this into a finite dimensional picture. And yeah, the long-term goal is maybe to develop some of those ideas with Zakani and so on, but then in this finite dimensional picture, not so much in this infinite dimensional picture. This is also one reason, I would say, why we don't bother so much about developing technicalities about infinite dimensional manifolds. I'm glad nobody asked, but so we're not doing Frechet manifolds or anything of that sort, even though it is certainly possible, and for some applications probably it's also necessary. But so long as one's just dealing with two forms, one can get by with diffeological spaces, but even that we don't really bother because in the end we're translating everything into a finite dimensional picture anyway. So it seems besides the point to develop all the technicalities in infinite dimensions. Yeah.
Maybe answering Nejla's question, one comment about the relation to JT, one way to probably, one mathematically relatively well-defined way to address the JT question, it's a correspondence between bulk and boundary, right? And the bulk, that's what Eckert was describing, right? That's some set of hyperbolic metrics with some conditions at the boundary. And the boundary story, that's basically what happens with that moment map. And sometimes you get an isomorphism, or sometimes you get a map with fibers being finite dimensional. So that may be that's one interpretation of this holography between boundary and bulk in JT. So that would be one possible interpretation. Maybe one more thing to add, right? Eckert mentioned in the beginning those wiggly boundaries, right? Which looks like an attractive and interesting picture. We somewhat oscillate, right? Sometimes we think it's simply nonsense, and sometimes we think, oh, who knows, maybe one should do further research and understand what it is. But as you have seen, we don't have any wiggly boundaries, right? So we just have a boundary at infinity and classes of metrics.
Well, maybe the way I was actually thinking about this, if you start out with some standard hyperbolic zero metric on the surface and you apply a diffeomorphism to it, you could look at the curves of constant geodesic curvature near the boundary. So initially they look nice and straight. So if you apply diffeomorphism, then of course they become wiggly. And so that was some of my thought, how the pictures are related.
Okay. Isn't it related to your k-1 at the beginning? You had this k of x1, which was
yeah, exactly, And I should have mentioned that this formula for the mode map that we had was actually somewhat inspired by a formula that we saw in the physics papers. So the fact that this expression, this coefficient of the geodesic curvature, the coefficient of y squared has something to do with Virasoro and Schwarzian derivative that we saw in one of the physics papers.
Okay. Any other questions?
Let me ask you a quick question. So your statement is that you have a kind of moment map to this Virasoro structure. So then does this Virasoro has a central term or central extension? I think this is generic about this vector field.
Virasoro is the central extension, but so what's going on here is the mode map takes values in this level 1 set of the dual of the Virasoro algebra. So what this means in practice is that the Virasoro group doesn't really act. So you could say the central circle of the Virasoro group acts trivially with mode map 1. So it's only the action of diffeomorphism that one actually sees. But still, it's in some sense, it's Virasoro because the mode map is equivariant for this. It has this. What's called this? This extra term with Schwarzian derivative, right? It's an affine action.
May I add one phrase?
Please.
So what Eckert wants to say is that the central charge is 1.
In this situation?
Yes.
Okay.
Sorry. Is it okay? Okay. Any further questions? Okay, people, let's thank Eckert again.